Okay, this video is about hydrolysis, about carboxylic ester hydrolysis. So if we notice in the examples we did before in Fischer esterification on our previous slides and pages, that the arrow was a double arrow. This real equilibrium arrow, where it's got a fishhook to the right and a fishhook to the left, is our equilibrium arrow. And this indicates that the reaction is reversible. So the reverse of the Fischer esterification of the condensation, the reverse is called a hydrolysis reaction. So ester hydrolysis takes that product from Fischer esterification, that lovely smelling ester that we made, and it reverses it. So it takes the ester and water and takes it back to the carboxylic acid plus the alcohol. So ester hydrolysis reactions always look like this. Ester plus water gives carboxylic acid and alcohol. A general hydrolysis reaction always looks like this. You have a large organic molecule and water reacts to form a smaller organic molecule and another smaller organic molecule. So really, we just need to talk about the reverse of Fischer esterification and going back to the carboxylic acid and the alcohol. So if we have an ester, what we're going to do is break that ester bond. So this ester is CH3, C double bond O. That C is bonded to an O, CH2, CH3. And then the ester reacts with water in the presence of an acid catalyst again, like H2SO4. And it makes the carboxylic acid, CH3, C double bond O with the OH, plus the alcohol, H bonded to O, bonded to CH2, CH3. So we're just sort of breaking that ester bond. We are taking the CH3C double bond O, putting the OH back on it, taking the other side of the ester, that's going to become the alcohol side, OCH2CH3, putting the H back on it. So we're taking water and putting the H back on the alcohol and putting the OH back on to the ester to make a carboxylic acid. So notice that the reaction requires an acid catalyst, just like before, in this case, H2SO4, and for this reason, these reactions are sometimes referred to as acid-catalyzed hydrolysis reactions. It's really just Fischer esterification in reverse. Because this reaction is reversible, it can, Fischer esterification can go forward to the ester, or it can go and reverse back to the carboxylic acid and the alcohol. That means if we're conducting an esterification, we have to push it to the ester. We either have to remove the product, add more reactant, do things to push it to product. So the point is that we can then sort of manipulate that back and forth as the chemist, forcing the reaction to go to completion in the desired direction. Okay, so let's look at an example. CH3, then it says we have CH2 and 8 of them, and then it's C double bond O, and then bonded to O and bonded to CH3. So we need to break the C bonded to the O between in the middle of the ester. We need to break that ester bond. We need to recognize that this is an ester, recognize that we're going to break that ester bond using that water. Okay, so when we do that, let's just copy the carboxylic acid part, CH3, CH2, there are 8 of those, bonded to C, double bonded to O. Now we have to break that ester linkage and put an OH on there. So now we've gone back to our carboxylic acid. Plus, we need the alcohol. So we put the H back on to the O, CH3, so that we end up with CH3OH, or methanol. So we've just reversed our reaction here. Okay. In this example, we've got a cyclohexane, and then it's bonded to CO2, CH2, CH2, CH3. And it's reacting with water, and it's got that acid catalyst, or that H2SO4. Okay, so we might want to redraw this, recognizing that CO2 is shorthand for a carboxylic acid, right? We want to be able to recognize those different forms. Excuse me, it sounds like we spent a lot of time on carboxylic acids. Of an ester. Let's just scratch that, ester. We want to recognize that. I talk a lot about how CO2H is shorthand for a carboxylic acid. CO2 in the middle of the carbon chain surrounded on either side is shorthand for an ester. We do look for it in the same way. Okay, so it would be helpful to write that out since the shorthand can be confusing, especially if it even got me for a second. Okay, so let's rewrite out CO2 as C double bonded to an O. So first we've got the cyclohexane bonded to a C, double bonded to an O, bonded to an O, and then we can copy the rest. CH2, CH2, CH3. We're just sort of recopying that ester. Again, we want to break that ester linkage, break that C to O bond. So we'll end up with the cyclohexane with a C double bond O and then an OH. There's our carboxylic acid. I was getting ahead of myself. And then we'll have the H added on for the alcohol to the O, which is then bonded to CH2. And there are two of those. And then CH3. Sorry, I'm just running a little short on room here. But if we want to rewrite this alcohol maybe down here, it's just HO, CH2, CH2, CH3. Maybe that's a little nicer, but it's supposed to be the same thing. So we've got our carboxylic acid and our alcohol. Okay. One more here. CH3, C double bonded to an O, bonded to an O, bonded to CH2, 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 CH3. So break that ester linkage again between that C and that O. We'll end up with CH3. Oh, by the way, it says plus water and our acid catalyst here. So we have our acid catalyst as well. And we'll do our double-headed equilibrium arrow. Now let's go for those products again. CH3 bonded to C, double bonded to O, and then bonded to OH. That'll be our carboxylic acid product. Plus, we'll need our alcohol. So in our alcohol, we'll have HO, and then we have CH2, 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 and finally CH3. So it's really important that the other parts of the carbon chain remain unchanged, that all we're doing is breaking that ester linkage, but we're copying the parts that are going to make it carboxylic acid and that are going to make it an alcohol. Okay, so in each case, we had carboxylic acid and an alcohol as our products of the hydrolysis of that ester. So I just think of ester hydrolysis as the exact reverse of Fischer esterification. It is Fischer esterification in reverse. We have to study both because that is a reversible reaction, and we'll have to push that reaction in the desired direction using all of the techniques at our disposal, like removing the product we want, like adding more reactant, those types of things that can drive a reaction forward.